Hi everyone. Today I want to present a paper called DKN, a Deep Knowledge Aware Network for News Recommendation. And this paper is published on WWW 2018. My presentation is divided into three components.
Sorry. I'm seeing your face. I'm not seeing the screen. Or am I doing something wrong there?
What's wrong? You don't see the each slide.
Technical, right? Okay, let me try again.
Yes.
Okay.
So please do.
Today I want to present a paper, DKN, Deep Knowledge Aware Network for News Recommendation. And this paper is published on WWW 2018. My presentation is divided into three parts. Let's go with the first part, introduction. Usually news recommendation is everywhere. Maybe every day we use some app to read some news. Sometimes maybe there are a lot of news articles every day. Maybe it's not possible to read every news article. So maybe there is a way to personalize the news recommendation so that we can receive the news articles that we are interested in. So this is the demanding for the news recommendation. News recommendation aims to provide personalized news recommendation to users. And on the other hand, there is another kind of data called knowledge graph. Knowledge graph can capture semantics among the entities on knowledge graph. For example, on the figure you can see on the left-hand side, there is a phone showing a news article. But for example, if you are interested in the second news article, Boris Johnson has want Trump to stick to the Iran nuclear deal. So in terms of this news article, it has several entities. Now we extract the entities from this news article. We extract Boris Johnson. We extract Trump. We also extract Iran and nuclear. And then we map this news article into several entities in the knowledge graph in the middle. And by the semantics on the knowledge graph, for example, on the left-hand side, you can see Boris Johnson is a politician. And politician usually appears in Congress. And Congress is also associated with another news article. North Korea EMP attack would cause mass US starvation, says congressional report. So by this semantic relationship, we can transfer from the first news article that you have already read to another news article maybe you are likely to be interested in. So that by this way, we can make news recommendation. And the role of knowledge graph in the middle is trying to transfer the knowledge from one news article to the other, so that by the semantic capture, we can know how you are interested in the potential news article. And the goal of this paper is trying to integrate both knowledge graph and news recommendation into a consistent model so that we can use knowledge graph data to make personalized news recommendation. Now let's turn to the model part. I would like to present the pre-processing first and then introduce the model architecture. The first problem is, given a news article, given a news title, how can we extract the entities from the news title? In terms of this paper, the authors use existing entity linking tools to extract the entities from news title. However, I would like to argue that the entity linking here is not the contribution of this paper. This is only the pre-processing of the data. So in terms of entity linking, they use existing tool. For example, on the left-hand side, you can see there are several news articles. The first one is related to Trump, and the second one is related to Apple, CEO, and so on. By the entity linking tool, we can extract the entities from these news articles. You can see on the right-hand side figure, Trump, Las Vegas, Apple, CEO, and so on. And the next step is to use knowledge graph, or we construct a knowledge graph based on the entities we extract from news articles. We also use some existing knowledge graph from some commercial companies to construct our own knowledge graph. Now we have already extracted the entities from news article already. And then we map the extracted entities to the existing knowledge graph. And then we only maintain the entities in the knowledge graph that we are interested in, and we remove all other entities so that we can only extract a sub-knowledge graph that we are interested in. Maybe the whole knowledge graph is very big. We are not interested in all the entities. We are only interested in several sub-graphs. For example, in terms of Trump, we can map Trump to the vertex on the right-hand side knowledge graph. CEO, we can also map to the right-hand side vertex, and so on. Yeah, so in terms of this paper, the authors use Microsoft Statutory Knowledge Graph. However, the third way to preprocess the data is that not only do the authors maintain the vertex we are interested in, we also maintain the immediate neighbors of those vertices. Immediate neighbors are also called contexts of entities. For example, you can see the figure on the top right corner. If the entity we are interested in is a Fed club, but there are some relationships between Fed club and all other entities, and all other entities are immediate neighbors of this Fed club, we also maintain other neighbors of this entity, and we remove all other entities that are not immediate neighbors of Fed club. We only maintain immediate neighbors. This is the way we construct knowledge graph. We maintain these vertices entities, and we remove all other irrelevant entities. And let's go back to the original example. You can see the right-hand side figure, right-hand side subgraph. Now we have already mapped some entities to existing knowledge graph. However, you can see there are two context entities. They are not any entities from the existing news article, but they are neighbors, immediate neighbors of existing entities. That's why we still maintain those vertices. Now we have already extracted the entities and the knowledge graph from news data. Now let's turn to the model architecture part. This is the overview of the model. The whole model can be divided into three components. The first component is called KCNN. The second component is attention network. And the third component is a prediction network. I will introduce one by one. Let's first of all go with KCNN, also called knowledge-aware convolutional neural network. The goal of this network is to learn representation for a news article. Suppose we have several words within a news article. And in this paper, the authors use title of news to make recommendation. They don't use any content, the main content of the news. They only use title. And suppose the title has n words, and then we put word embedding one by one into a word embedding matrix. Each column corresponds to one word, and each row corresponds to one dimension. You can also see the example on the right-hand side. You can see, suppose the sentence has several words, then we put the word embedding one by one into a word embedding matrix. Each column corresponds to one word. In addition, we also have entity embedding matrix. Remember, we have knowledge graph. Each word in the news title is also associated with an entity in the knowledge graph. Correspondingly, we also put the entity embedding one by one into an entity embedding matrix. Similarly, you can see the second map of the matrix. The second map corresponds to entity embedding matrix. Each column corresponds to one entity. In this paper, they also introduce context, right? So contexts are the neighbors of entities. So in this paper, the authors take the average of those neighbor embedding as the context embedding of the entity. And then we also, on the third layer, we also put the entity embedding as a matrix. Each column corresponds to one entity context. Suppose one word in the news title doesn't have any associated entity or entity context, then we just use 0 vector here. So this is how we put 3 layers of embedding matrix. And the next step is to use these 3 layers to learn news representation. The first step is convolution. Now suppose we have window size of 2. Suppose red is the filter, and the window size of this red filter is 2. So we can see for title embedding or word embedding, we have 2 words. Similarly, for entity embedding, we also have 2 entities. For context, we also have 2 context embeddings. So in total, we have 6 embeddings. So we concatenate these 6 embeddings into a single vector. The first two embeddings are word. Second 2 embeddings are entity, and the third 2 embeddings are context embeddings. So the total dimension of this concatenation is 6D. We multiply this 6D by another learnable parameter with length of 6D. The multiplication, the product of these 2 results should be a single real value. And we also add a Bayes B. And we use a nonlinear activation function f to transform them into another single real value. We call it Ci. So this is why in this figure we can see from this red filter, we can see this is Ci. We output a Ci value. Now we can see in terms of the red filter, we can move forward. The next step is to W2 and W3. The next step is W3 and W4 and so on. We move this red filter forward until we reach the last word in the title. So in terms of the red filter, in total we have 6 real values. That's why we have 6 values here. Each row has 6 values. And max pooling. Now we have 1 row of red embedding. And now, in terms of this row of red embedding, we take the maximum value of weight, and then we can get the first one of the final embedding, the first dimension of the final embedding. Max pooling, we take the maximum value of this row. However, you can see there are 3 red filters. All the red filters have a window size of 2, and there are 3 red filters. That's why we have 3 rows of embeddings here. Similarly, for the blue filter has window size of 3. So we have 4 blue filters. That's why we have 4 rows of blue embeddings here. Each row corresponds to one filter. And then for each row, we use max pooling. And then in total, we have the final representation of news article, and the dimension of it is 7, because we have 7 filters in total, 3 red filters and 4 blue filters. Yeah, so this is why I say the embedding of news, I use T to represent C red 1, C red 2, C red 3, C blue 1, C blue 2, C blue 3, C blue 4. Okay, and the parameters of different filters are different. Now from this component, we can see the input of this component is a news article, and the output of this component is an embedding of the news article. Now let's go back to the original model architecture. We can see, suppose this is a candidate news that we want to make recommendation, and then by this KCNN component, we can output the embedding of this news. Similarly, if a user has already read 3 news articles, 1, 2, 3. For each news article the user has already read, we also use this component to output the embedding of the corresponding news embedding. Now we can see 1, 2, 3. 3 news articles have 3 embeddings. And the next step is to evaluate the attention between the candidate news article and all the historical news articles. The attention network. The attention network is very easy to understand. For each historical news article, for example, for the first one, we evaluate attention between this one and the candidate news. We first of all concatenate their embeddings into a single vector here. we use concatenation here to represent. And then we put the concatenation into a fully connected neural network, and then we can get the weight of this pair of news articles. And then we can use A to represent. And now, because the user has already read 3 news articles, for each pair with respect to the candidate news, then we have 3 pairs. For each pair, we evaluate the attention value, and then in the end, we normalize them. We use softmax to normalize them. And then we take the summation. Because 3 news articles, we have 3 attention values. For each news article, we take the weighted summation using the weight of attention to output a single vector. And the single vector represents the user embedding. And in the end, we turn to the prediction. We also concatenate user embedding and the candidate news embedding into a single vector and put them into a multi-layer perceptron. And we can output the click probability by height. And then the final loss function has 2 components. The first component is basically the cross entropy. It's the cross entropy between the predicted click probability and the ground truth click probability. And second component is basically knowledge graph embedding. Because in this network, we use knowledge graph, and we need to know the embedding of entities. And the entity is basically height plus relation is equal to tail. And we want to minimize this relationship. So that's why we have another loss function, LKGE. We want to minimize this one. After convergence, we can make predictions. This is basically the model that we use to make prediction. If the probability is quite high, then we recommend this news article. Otherwise, we don't recommend this news article. And there are 2 experiments. The first one is recommendation. In this paper, they use only 1 data set. This data set has these several number of users, several number of news articles, and so on. And they also had 4 different sizes of filters, 1, 2, 3, 4. And each size also has 100 filters. So in total, we have 400 filters, which means the dimension of news embedding is 400. And then we can see the recommendation result. They use 2 evaluation metrics. One is F1. The other one is AUC. In terms of the model proposed by this paper called DKN, the model outperforms all other baseline models. And here minus means we don't use knowledge graph. We only use the user item interaction data to make recommendation. And now we can see with knowledge graph can indeed improve the recommendation accuracy. Now let's also turn to the analysis of this model. The first analysis is in terms of the dimension of embedding. Now we can see K represents the dimension of entity embedding, and D represents the embedding of dimension of word embedding. And we can see maybe in terms of this setting, when the entity embedding is 100 and word embedding is also 100, the performance is the best one. If we further increase word embedding, then performance decreases, maybe because of overfitting problem. And for the second analysis, we also have window size of filters. Previously, we used 1, 2, 3, 4 as window sizes. And we can also change window size. And then we M here, different color represents different number of filters. And we can see if we increase the number of filters at the beginning, we can improve the performance because we can use more filters. The more filters we have, the more flexible the model is. But if we further increase the number of filters, the performance decreases. That means overfitting problem happens. Yeah. And the second analysis is evaluation analysis. In terms of DKN, if we remove both entity and context embedding, that means we don't use knowledge graph, or we waste both of them, then this is the performance. But if we only use entity embedding, but we don't use context embedding, then this is performance. By comparison, we can show context embedding is indeed useful. If we compare with the third one, if we only use the context embedding, but we don't use entity embedding, then performance further decreases. That means entity embedding is also useful. If we remove both of them, that means we totally don't use knowledge graph component. The performance further decreases. That means knowledge graph is indeed useful. And there are 4 different ways of knowledge graph embedding. And we can see the last one is the best one. Yeah, if we further look at the attention mechanism, because we have attention network, if we have attention, then the performance is 68.7. But if we remove attention mechanism, the performance decreases. That means attention mechanism is also important. Yeah, that's all. Thank you.